postdoctoral scholar at JPL. Before that, she got a PhD at Cornell. So today she'll be talking to us about weak lensing. Thank you, Anna.
Thanks, Adrian. So yeah, I'm going to talk today about some recent work I've done with these collaborators here. So it's Tim Eifler, Wayne Hu, who's also in Chicago, and then Michael Mortensen and Jason Rhodes, who's my advisor back when I worked at JPL. And please feel free to ask questions as I go on. So here's a quick agenda for my talk. So just in case, I'm first going to review quickly weak gravitational lensing, which is mostly what I work on nowadays. And then I'll review the current state of cosmological model building, and then spend the majority of time talking about my recent work on determining how well future weak lensing observables will be able to constrain or rule out these models. And then I'm going to conclude by advertising what I believe to be the future of weak lensing, or at least the future of my career in weak lensing, which is the Euclid satellite. So cosmological observables are typically divided into two basic overlapping categories that I'm going to be referring to throughout this talk. So there are first observables that tell us about the smooth background component of the universe. So if the universe were completely homogeneous, this first part is all we have. And so we can characterize it in terms of, first of all, the current expansion rate, h0. But then we can measure how has that expansion rate been changing over time. And we can do that using what we call standard candles and standard rulers. So standard candles, like Type 1a supernovae, are objects where we feel like we understand their intrinsic brightnesses well enough that we can determine their distances based on how bright they look. And then we also have what we call standard rulers, such as baryon acoustic oscillations, which are objects where we feel like we understand their intrinsic sizes very well, so then we can measure their distances based on how big or how small they look. But fortunately for us, we don't live in a homogeneous universe. Our universe has perturbations. It has stars and planets and astronomers and cats. And indeed, we can learn a whole lot more about physics of the universe by characterizing the way perturbations grow on top of this smooth underlying background. So first off, we have the initial conditions, or at least as initial as we can see from the cosmic microwave background. And then we can also measure the current state of affairs by just measuring the current matter power spectrum through, for instance, galaxy surveys. And then we can also measure how did those structures grow, what was the growth function like from that CMB period up until now. And for the rest of this talk, I'm going to focus on weak lensing. So weak lensing works like so, in a highly simplified way. When we look at a field of distant galaxies, those galaxy images that we're seeing have been gravitationally distorted by all the matter that's been lying along the foreground between us and those galaxies. So if we have some projected gravitational potential psi along the line of sight, the image that we see is equal to the unperturbed image multiplied by this distortion tensor that I call A here. And in the limit of small distortions, it can be written as an expansion around the identity matrix, and we call this component here the convergence kappa, and that corresponds to an overall magnification of the image. And then we have what we call the shear gamma, which is a 2D stretching of the image. And it turns out that the shear is more straightforward to extract from an image than the magnification or the convergence. And that's because if you try to measure the magnification of an object, it's harder to know exactly how bright it was supposed to be. But in terms of whether or not an image has been stretched, we can rely on the assumption that on average galaxies will be round. So if you took all the galaxies images, the image of every galaxy that we can see, you stack them all up on top of each other, we expect that we get a circle because we expect galaxies to be randomly oriented with respect to us. So we extract this shear by looking at galaxy shapes and averaging them over patches of sky. So for instance, you look at some patch of sky that contains a lot of galaxies, hundreds or thousands of galaxies, and if there's no stretching of the image, no shearing, you would expect those galaxies to be randomly oriented. But if there has been a shear, we expect there to be some overall preferred alignment.
Just a question here.
Yeah,
It's
definitely.
maybe a naive question. Is this a problem for higher order statistics then, that assumption? Like if you're doing a 2-point correlation function or something like that?
Why would that be a problem?
Because they're not spherical on average in the first moments.
That what aren't spherical? Oh, the galaxies.
galaxies, yeah.
Galaxies aren't spherical. No, it doesn't end up being a problem. What we do is when you measure, what we end up getting from this averaging of the galaxy shapes is you get a shear map. So then you take that shear and you cross-correlate it or auto-correlate it. So it ends up being a problem in that you need to have really good statistics to extract the shear. You can't just have a very sparse field of galaxies. You'll learn absolutely nothing from that. So that's where it's a problem. You have to have a lot of galaxies, and the image has to be densely populated with them because it is a statistical measure where you do have to average over the shapes. So if galaxies were intrinsically all round, this would be way easier problem to solve. Statistics would be far better. All the error bars and everything I'm going to show would be way smaller.
How many galaxies do you need for the statistics to start being reasonable?
So it depends on a lot of aspects of your survey, but it can be hundreds to thousands, depending on different surveys. You'll have different intrinsic ellipticities of things. You'll have if you have seeing space versus ground, things will be different. But you need a lot of galaxies. And so I'm going to talk about later the Euclid satellite, which is going to image 2 billion galaxies.
Wait, is your statement that galaxies are spherical on average? Is that only true for elliptical galaxies? Or?
Well, so I'm not saying that galaxies are spherical on average, but I'm saying if you look at the image of galaxies on the sky as they're oriented with respect to us, if you stack them all, you get a circle. So galaxies could no galaxies are spherical. You can't have a spherical galaxy. It's never going to happen. But if you have, even if galaxies were, a bunch of weird shapes, we're just assuming that on average, the average shape will be around. There's no preferred orientation for a galaxy to be in. Any other questions? Yeah, and depending on what types of areas you're looking at, galaxies will be more or less round, actually. So if you're interested in looking at, say, a galaxy cluster versus a void, galaxies are going to tend to be more elliptical in a void than they are in a cluster. They tend to be redder and rounder. And that might affect the statistics of how you analyze your data, but it's not going to affect the basic assumption that on average they're oriented, but just that they're oriented randomly with respect to us.
Could you align it differentially with filaments or something?
They can be, so that's a big problem in weak cleansing. It's called intrinsic alignments, and so that's the idea that galaxies will have a preferred alignment in different regions of the universe just because they're aligned with some sort of filament. They formed in the same tidal field, and that is one of the biggest systematics for weak cleansing. And I'm completely glossing over it right now. Okay. So to do this, you need to have, like I said, good statistics. So you have to image a lot of galaxies. This is necessarily a statistical measure. And you also need high resolution imaging. We need to have as accurate as possible on a picture of what these galaxies look like. There are lots of other things that can distort galaxies. So there are lots of systematics. There's the atmosphere for a ground-based telescope. You can have inefficiencies in your detectors that can cause trails in the images. And all those things can mimic a shearing signal. And so you want to either avoid those things in the first place and or find strategies to remove those non-gravitational distortions from your images. So the most direct thing that you can do with weak lensing is mass maps. So I'm showing one of the first such maps from Massey et al. 2007. So in this image here, blue is the stellar mass density, yellow is the galaxy number density, red is X-ray, and the contours are the weak lensing map. So you have, so the colors are different tracers of where the baryons live, and then the contours are showing us the total matter distribution that we get from weak lensing. And this was done using imaging from the Hubble Space Telescope from the Cosmos Survey. So we see that the dark matter distribution traces the visible matter distribution. This was a big breakthrough in that paper. More useful in terms of cosmological constraints are, of course, the statistics of the shear field. For instance, the two-point correlation functions and the power spectrum, as I'll be talking about later. And then also, if we have redshifts for our galaxies, which we do need anyway to do any of these measurements, we can bin them in redshift and then do tomography. So each redshift bin of these galaxies we're looking at that are gravitationally distorted gives us a picture of all the matter that's lying between it and us. So this sheet of galaxies here is all the lensing happening there is for matter in front of that. Same thing for this one. So every bin gives you a picture of the matter distribution between, say, 6.5 billion years ago and today. So in this way, we learn about the expansion history and structure growth and the interplay between the two. So here's the current state of the art in space-based weak lensing observations. So I'm showing here a plot from Travick et al., 2010. So this is lensing from the Cosmos Survey, which again is HST imaging. And this plot is the two-point correlation function, one of the two of them, as a function at angular scale. And there are 6 redshift bins that they've separated galaxies into. Bin 1 being the closest to us, bin 5 being farthest away, and then bin 6 is a wide redshift bin that encompasses everything. And so all of these points here are for the cross correlation between one individual redshift bin and the entire sample. And the points are the data, and then the lines, corresponding lines, are from the best fit cosmological model. And this is an excellent proof of principle, but it's very crude because we don't have that large area survey that we need right now, at least not from space. So this survey is only 1.64 square degrees, whereas compare that to what we would expect with the Euclid survey, which is 15,000 square degrees. But one thing that this study does do right is that it has a small stable PSF that you get from space. Just to show you the difference from space and from the ground, here's a galaxy's image with HST, and here's what it looked like from the ground. So you see that there's been a large image distortion caused by the atmosphere. And if we're looking for 1% level shape changes of these galaxies, you have to find some way to remove that systematic, which is being done, for instance, in the pipeline of the CFHTLS survey. But for a space-based survey like this, the problem becomes easier, and then it becomes more of a problem of observing area.
So can you just tell me what this plot is one more time?
So this is one of the two-point correlation functions of the shear field.
Okay.
So the shear correlation function, and these are all cross correlations between some redshift bin and then the total sample. And they're the 5 redshift bins going away from us, and the total sample is bin 6. So, for instance, for the bin closest to us, bin 1, cross-correlating with the whole sample, you get these X's, and then this corresponding line is the theoretical prediction for the best fit model that they get from this.
But not much correlation.
No. And this is from a very tiny sample size, and things start to get bad as you go to smaller scales because we don't understand the small scale matter power spectrum as well. So as you go smaller and smaller scales, baryonic physics becomes important and other things like that. So I believe they actually threw out the data from the smallest of scales, and they're not shown on this plot just because we don't understand the physics of structure formation at those scales. Okay, so in order to get any insights from these observations, we need some models to work from with tunable parameters so we can fit to the data. So the baseline model that I'm going to be using here is called the standard flat lambda CDM model. So it consists of cold dark matter, some sort of non-clustering dark energy, and a few atoms, and started with Gaussian fluctuations, which then evolved according to general relativity. And here's why we like this model. Pretty old plot, but basically this is still happening. We have all these different types of cosmological observations. It all depend on all sorts of different things, and if you take this very simple 6-parameter model and you fit it to all these data sets, we find that the contours tend to line up, all these ellipses, and so that's why it's often called the concordance model. Now, as all these data sets are getting better and better, we're finding these ellipses are getting smaller, and there's a little bit of some tensions being created right now, but for a long time, there's been really, really good agreement. And so these 6 parameters are all you need to describe this model. So there's the baryon density, the cold dark matter density, parameters dealing with reionization and decoupling, and then parameters that tell you the initial spectrum of fluctuations at the CMB. So, but like I said, there hasn't been, there's starting to be some tensions between these data sets. And indeed, we would expect that to happen eventually because this model is fairly oversimplified. And there are lots of different ways in which you can extend it. And here are a few ways that I'm going to be looking into in this talk. So first of all, we could introduce some sort of overall spatial curvature into the universe. Also, dark energy could be dynamical. It could be some function of redshift as opposed to being a constant. We could perhaps have early dark energy, which is exactly what it sounds like, dark energy that's important in the early universe. Baryons, not really a model extension per se, but it's usually something that people have traditionally ignored in doing these analyses, but now that we're able to probe smaller and smaller scales, they're becoming more and more important. And then another thing that's been interesting lately are neutrinos, their mass, and the number of species, neutrino species, because there's been lately some evidence that perhaps there might be more neutrino species than we previously thought. So one novel way to test these models is by exploiting consistency relations between the 2 types of observations I was talking about before. The observations dealing with the smooth background of the universe, and the observations dealing with the perturbations that grow on top of that background. And it turns out that if you know the expansion of the smooth background and you have the initial fluctuations from the CMB, that itself is enough to uniquely determine the 6-parameter set. So for instance, if we knew exactly the expansion history of the universe, we knew exactly the cosmic microwave background, that would tell us these parameters. And then once we had these, we could then predict exactly the statistics of the perturbations that we would expect today. So there's this consistency relation here. If we have one of these types of observations, we can then predict the other one. And this is a great thing to do right now, especially for weak lensing, because we currently have very nice data sets on this top line of observation. But in terms of weak lensing, as I was showing before, we don't have this data yet. And we plan to have it soon. It's coming along. But in the meantime, it's a good idea to predict what we would expect within this model, and then see how those expectations change if we go through these various model extensions as I outline them. And this also becomes a very good framework for analyzing various theory systematics. For instance, knowing the nonlinear matter-power spectrum. How do certain uncertainties in that impact our ability to learn from these future observables that we're expecting? So this is the basic methodology. So like I said, we take these expansion history observables, and then so the local Hubble constant, baryon acoustic oscillations, and type 1a supernovae, we couple that with the initial fluctuation spectrum from the CMB, and couple that with some sort of cosmological model that is tunable parameters, like for instance the flat lambda CF model, or maybe we put in some of those model extensions. And then we use Cosmo MC, which is a public Markov chain Monte Carlo sampler, and then we can get predictions for any future structure growth observables that we want. So here I'm just showing an example. This is the growth relative to today as a function of redshift for the flat lambda CDM model. So the top panel is this growth function. The bottom panel is it's the basically top panel with the maximum likelihood prediction subtracted off. So this is the deviation from the maximum likelihood prediction as a function of redshift. And the solid contours are 1 sigma, and the lines correspond to 2 sigma. And so, so in this way, we could then say, measure this growth function somehow, and then take our data points and plot them on here, and see if it's consistent or not. And if it's not consistent, then that means we've falsified the flat lambda CDM model. So this method is used in these papers here. So in a bit more detail, these are the data sets that I use. And again, there's a six parameter set for the flat lambda CDM model. And then we're going to extend that model in various different ways. And one way in which we do that is we allow for dynamical dark energy. And so we allow the dark energy equation of state, W, to become a function of redshift. And we do that by expanding it in principal components. And we use 10 principal components to do that. And so combining the parameters with the data, you get a joint posterior distribution for the parameter set. And then from that, you can derive the statistics for all sorts of observables. So in order to compute weak lensing observables, we need the distance redshift relation, the growth function, and the redshift 0 matter power spectrum. And then say you're looking at some particular survey configuration, you need a source redshift distribution, N of Z, and this is a very simple, widely used model for the number density sources as a function of redshift. And then you can compute, for instance, the cosmic shear power spectrum, which is what I have here. And I know it has a kappa, but to linear order, the power spectrum of convergence and shear are equal. So in this equation here, this is an integral over redshift, going away from us, of basically the full nonlinear matter power spectrum. And there's a distance weighting function there. So you're taking a distance-weighted integral of all the matter lying along the line of sight. And then that gives you the power in shear fluctuation. So some predictions from this. Here is the weak lensing shear power spectrum that we get from the flat lambda CDM model for a model space-based survey and a matter of ground-based survey. So space-based survey, we're trying to simulate basically the cosmos surveys as shown before. And from the ground, we're looking at surveys like the CFH TLS survey. And again, as before, the filled region is 1 sigma and the lines are 2 sigma. And the predictions from space are the gray, and from the ground are in blue. And then on the bottom panel, I'm showing the fractional difference from the maximum likelihood prediction. So this is to give you a better idea of how wide those prediction bands are. So we see that the space curve is higher than the ground curve, which is what we expect. You get more shear if you're doing a survey from space than you do from the ground, because your redshift distribution of your galaxies is pushed out to higher redshifts. A higher redshift galaxy is going to be sheared more than a low redshift galaxy. So that's what we'd expect. And the uncertainties in these predictions, so the width of this, has nothing to do actually with weak lensing or any weak lensing observational systematics. Rather, it comes from uncertainties in the expansion history and the CMB data we use to make these predictions. So if we understood the expansion history in the CMB, if we had perfect data for those with no uncertainties, we would be able to predict this perfectly, and this would just be a line around 0, and this would just be a curve somewhere in there. But it's because we don't know the expansion history of the CMB exactly. It's because there are errors in that there is an uncertainty here. So that uncertainty comes mainly from the shape of the initial power spectrum that we get from WMAP. So the amplitude and the scalar index feed in to give us our uncertainties in what we would see in the future with cosmic shear.
What about dust?
Dust?
Yeah.
I honestly, I don't really know how that feeds into this. So we were just using the Cosmom C with WMAP as from the Lambda website. So I'm not sure how that treats dust or how big of an uncertainty dust is. So, but
There could be a lot of behavior in
there could be, yeah. I'm really unsure of how the CMB people analyze their data with respect to dust, but we can talk about it later. So assuming that we don't have, assuming that we don't have that there could be uncertainties, like for instance with dust or something else that we just don't know right now, and so then that could change these predictions. But assuming that that sort of stuff's not going on, then when we get data from the Planck satellite, these prediction contours are going to shrink. So Planck is going to get us this initial power spectrum with even greater precision, and so what that's going to do is it's going to improve our predictions here. And so not to be confused with the gray up there, but this gray is just how these blue contours will shrink if we have using data from Planck instead of from WMAP. So we find that our predictions get better by a factor of 2 or 3.
This was some BAO from Neutrinos Is.
So this is using BAO from SDSS. So this is using, this is not using the new Wiggles or Boss points. This paper is from 2012, but I'm going to show some results later where I do use all the new BAO data. That's a good question. So the correspondence with actual data points is easier to see with a 2-point correlation function. So this is the same 2-point correlation function I was showing data for before from the Cosmos survey as a function of angular scale. And so again, I'm showing predictions from for our mock space and ground-based surveys. It's the gray and the blue, again with 1 sigma and 2 sigma contours. And then plotted on top of that are all these data points that the current state of the art when we wrote this paper last year. So from ground, it's magenta points from Benjamin et al., and then from space, it's black points from Shrevek et al. And we see there's 2 kinds of competing uncertainties here. There are uncertainties in our predictions, which give us the width of these error bands, which they can come from uncertainties in the CMB and the distance scale. But there are also uncertainties in the data that give us these error bars, and that come from weak lensing systematics. And right now, there's no, everything is concordant with everything else, as you would expect. You would know if weak lensing had ruled out the flat lambda CDM model by now. That would have been big news, and we're not showing anything that anyone didn't already know. So weak lensing, current state of affairs, completely consistent with the flat lambda CDM model. But part of that is because these measurements are, like the error bars are so large. So with future weak lensing surveys, these error bars are going to shrink dramatically. So for instance, Euclid is going to have 1,000 times the area of this Cosmos survey. What that does to the error bars depends on how much better we get at measuring galaxy shapes before Euclid launches. But also, these prediction contours are going to be shrunk by Planck.
So it looks like there's actually tension between the data and the observations here already. Is that not the case? Like, is it the data or the?
It's
probably,
the data.
It's probably not the theory. It's always the data's fault. Right?
Well, so since this was done, CFH-TLS has come out actually very recently with a new release of their data, of actually their full 154 square degree survey with a new pipeline analysis. So they actually had some systematics in their analysis that they've been able to mitigate since then. So you're talking about like this upturn here.
Yeah, it's not even
yeah.
monotonic in the data.
Yeah, so that's a systematic in the CFH-TLS data that's since been fixed. but yeah, good eye. So if this data did not overlap with the predictions, then that should be a smoking gun for some sort of model extension. So what happens to our predictions when we extend the model in some way? Well, on this top panel, I'm showing what happens when we now allow the curvature to vary. So the gray hash region is what I was showing before for a flat model, and then the blue is what happens when we allow for non-flat models. We see that not much happens, and that's to be expected because WMAP7 has actually very well constrained the curvature of the universe. So that's not really much of an unknown. But then if we allow, we then move from having a cosmological constant to allowing dynamical dark energy, as in the middle and lower plots. So gray is what we had before, and blue is now what happens if we allow the dark energy equation of state to be broken up into those principal components. We see it now, we get less shear. So we get this bias, this shift of our prediction contours towards having less shear in the universe. And that's because in all of our models, we're saying that we're not allowing phantom dark energy models, which is where the equation of state would go below -1. So what we're doing is we're taking a model where W is -1 for cosmological constant, and now we're allowing it to vary, but we're still requiring it to stay above -1. So that's what's causing, since we're only allowing the dark energy equation of state to go in one direction, that's only allowing this contour to go in one direction. And so you would get different results depending on what kind of dark energy models you would be allowing in your fits to data. But if you make that restriction, this is what happens. And so if you were to have a shear, with your data, your eventual weak lensing data, you'd find a shear excess, that would then be evidence for some further model extension. That would mean that some assumption that we're making in our model must be wrong. And so one of them could be that not allowing phantom dark energy thing could be that W would go below -1, but it could also be that we have some sort of, say, primordial non-Gaussianity, or some sort of baryonic cooling, or maybe modified gravity, just to list a few. So what about baryons? So baryons are good news and bad news for weak lensing. So good news because astronomers are made of baryons. Bad news for basically every other reason. So it's very difficult to simulate small-scale structure formation in the universe because baryonic physics is just so rich and complicated. And this isn't a problem for large-scale weak lensing. So I'm showing here again our predictions for the shear power spectrum. And again, it's this deviation from the maximum likelihood model, so that's why it's centered around 0, as a function of multipole. And for very low multipoles, below L of a few hundred, this isn't a problem. But as you get to smaller and smaller scales, baryonic physics have a bigger impact on the matter power spectrum. And this shear power spectrum is really just an integral over the matter power spectrum. And so any uncertainties in the matter power spectrum feed into an uncertainty in the shear power spectrum. So I'm showing here is the effect, so in red and also gray, but they lie on top of each other, is how our prediction contours shift when we use the results from one particular small-scale structure simulation, Vanderveld et al. 2011, where they found that if they put into their n-body simulation, if they put in AGN feedback, that it leads to significantly reduced small-scale power. And that leads to significantly reduced small-scale shear power because they're directly related. And the effect is very large, even at only L of 1,000. And if we had used the model of Renzender and Krastov in 2008, where they put in baryonic cooling, you would find the opposite effect. You would find enhanced small-scale power because this cooling enhances the concentration of dark matter halos, and you would get the opposite effect where these contours will all shift upward. And while there's agreement on how to prescribe individually AGN feedback or baryonic cooling, there isn't consensus on how much of each needs to be put into a simulation to have it match the real world. So this is an ongoing work in progress with people who are doing n-body simulations of cosmic structure formation. But I'm just showing here just how incredibly vital it is to understanding our weak lensing observations that we understand the small-scale matter-power spectrum. And another thing that impacts weak lensing predictions is the physics of neutrinos. So there's been a lot of excitement lately about a possible fourth neutrino species, which is now actually slightly favored by CMB measurements from the South Pole Telescope and from WMAP 9. So WMAP 9 in its first version actually had a low and effective, but that was from a bug in their analysis. So I'll refer you to version 2, which is now in the archive. But now when they take WMAP 9 and they add in, they call extended CMB data sets like SBT and APT, and then they add in BAO and H0, they get a number of neutrino species that is higher, and it's only 2 sigma, but a little higher than 3. So there's this tiny little hint that there might be something going on in the neutrino sector that we didn't expect. So what would weak lensing say about this? So if I now take the model that flatland of CDM model I was using to make my predictions, and I now allow the number of neutrinos to vary, it shifts my predictions from the blue to the red. So it shifts everything up. And that's because when you get this extra neutrino in there, if you have extra relativistic species in the early universe, but you want to keep the CMB the same, you have to change other parameters to compensate for the extra relativistic species. So you actually end up boosting the matter the overall omega matter. What that does is that leads to enhanced structure formation, and it leads to enhanced shear. So for these plots I'm showing on this slide, I'm actually using updated data sets. I'm now using WMAP 9 and the new SBT data, and I'm using the new BAO data from Wiggles and Boss. So, yeah, adding an extra relativistic species actually shifts our predictions up. But now if you allow the number of neutrino species and the mass of neutrinos to vary, so if you, let's say you assume that all neutrinos, the 3 standard neutrino species you have all have degenerate masses, which is what they did in these papers as well, you find that the shear comes back down, so you get now the green contours, and that's because massive neutrinos stay relativistic longer, and they wash out small-scale structures. And when you wash out small-scale structures, you reduce the amount of matter power, and then you reduce the shear power. So therefore, there's this degeneracy somewhat between this model with these varying neutrino parameters seems to give us the same predictions as we get from the flatland CDM model. But that is a degeneracy that will hopefully be broken by Planck very soon.
And where are the observations the best right now? They're better at larger scales?
Better at larger scales, so yeah.
So where do the observations start? Where do you start to lose constraining power? I've forgotten in terms of the...
So around a few hundred is where you really need to understand baryonic physics, the effect on the matter power spectrum. Is there a question? All right. So in the few minutes I have left, I'm going to now talk about one avenue for getting some data, and that is the Euclid survey. So here's a brief timeline of the Euclid mission. So there was a theme in ESA's Cosmic Vision program, which is the Dark Universe mission. And there were 2 mission concepts that were jointly selected for an assessment phase, and those were Dune and Space. Dune being an imaging survey with weak lensing in mind, and Space being spectroscopic survey with BAO in mind. And then they were combined into a single Euclid consortium, which was officially selected in June of this year. And then in December of this year, NASA selected a U.S. team, a 40-person U.S. team to be basically donated to ESA to help work on this mission and to get funding for it. and I'm the lead of the theory group for that US team. And so possibly most important to you guys is the proposed launch in 2020. So the Euclid survey, so I mentioned before what we need for weak lensing. We need preferably high precision imaging, so we don't have to remove a very complicated PSF, and a wide survey, and we need accurate redshifts for our galaxies. And so the survey strategy is aimed at getting us all three. So we need two different surveys, a 15,000 square degree wide survey and a 40 square degree deep survey with high precision imaging, the optical, and photometry and imaging in the near infrared, along with near infrared spectroscopy. And this strategy is supposed to be optimized for both weak lensing and baryon acoustic oscillations, as were the original Dune in space. And of course, there's a ton of other stuff you can do with this data set, though. And just in terms of cosmology, you could study clusters and redshift space distortions and integrated tactical effect, etc. So just the mission, the baseline as it stands right now, is an L2 orbit and a fairly long 6.25-year primary mission. The telescope is a 3-mirror and astigmat with a 1.2-meter primary with 2 main instruments, so a visible channel and this near infrared channel. And here's more detailed information about this. So the wide survey being a step and stare with 4 dither pointings for step. The telescope being a 1.2 meter, and these 2 instruments, the visible and the near infrared. The visible instrument having one wide wavelength range, one wide filter between 550 and 900 nanometers to try to maximize just the number of photons that we get from galaxies, just so we see as many galaxies as we possibly can, with the goal of imaging 2 billion galaxies that are imaging them well enough for weak lensing surveys. And here being pixel size and spectral resolution. So scientific goals of Euclid are basically the scientific goals of cosmology, but using these two complementary probes of BAO and weak lensing, we're able to get at these questions from 2 different angles. So how does the universe begin? Why is the universe accelerating? What is dark matter? And what are the properties of neutrinos? And these are the main questions outlined in called the Euclid Red Book. And if you're interested in that or anything else about Euclid, I refer you to the website. Or feel free to come talk to me after the talk. So that's actually it. So in summary, we can use current expansion history data to robustly predict future structure growth data. And then with those predictions in hand, these future weak lensing observations could potentially falsify the concordance model or maybe even larger model classes. You could potentially falsify quintessence models and things like that. And the Euclid satellite will provide the space-based large area survey we need launching in 2020. So, thank you.
So do you have a rough order of magnitude for what the delta P over P uncertainty you expect from Euclid? Around L of 100? For this year?
No, I don't. It's actually a tricky question. So measuring galaxy shapes is very difficult, and there have been immense improvements in doing that over the last several years. In Euclid, it's not even supposed to launch for another 8 years. So a lot of depends on our ability to deal with weak lensing systematics. It's a very systematic written measurement, so I can't really give you a good estimate of that.
Since 2020 is still a ways off, what are people going to do? I mean, are people going to do anything from the ground that will be interesting?
Yes, they definitely will. Thank you for asking. So there's also the dark energy survey, which actually has already achieved first light, and I believe is taking data now. And that's a 5,000 square degree ground-based survey. It's from Chile.
That's good enough.
And that's, I don't know when they expect to have their first data release, but that's something that's happening right now. Another thing, another ground-based thing that's also not happening until 2020 is the Large Synoptic Survey Telescope, LSST. So that's also not until 2020. Another mission concept that hasn't been adopted yet, but hopefully will be someday soon, is the HALO, the High Altitude Lensing Observatory, which is an idea for a balloon-based lensing survey. And the good thing about that is that it can be fabricated and put up extremely quickly. So if that were to be approved, it would only be 2 years before we have the data set for that. And so that's something that's being proposed to the NASA balloon program. And there's a white paper on that on the archive, with Jason Rhodes as the lead author.
But you're not going to, with the ground-based stuff, are you going to do any significant cosmological constraints, or is that?
Yeah, I mean, I hope so. And so dark energy survey is not just for weak lensing. It's you're going to do a lot of things with that data set. But the hope is for so currently the largest area lensing survey is CFH-CLS, which is 154 square degrees. So this is 5,000. And I believe in order to really take advantage of that increase in statistical potential, they'll have to do a very good job at getting rid of systematics. And I'm not sure if how well that's going to work.
Well, what's the biggest systematic here?
What's the main?
Yeah, what's the main source of the systematic?
The atmosphere. So if you're doing any of this from the ground, the atmosphere is a big systematic. And the biggest problem with the atmosphere is not necessarily that it's a large distortion. It's that it's constantly changing, so it's a function of time and position.
You're trying to do more photometry than spectroscopy, isn't it? But it's that big of a problem.
It is, yeah, so it's going to distort. So
it distorts the elasticity measurements.
Yeah, so I mean, the way we remove the point spread function is we look at stars in the area, and we see how they're distorted, and then we deconvolve that. But if the PSF, if it's changing in different parts of the image, and it's changing with time, then it makes like dithering images. You can't do that. And so it actually does make it a lot more difficult to deal with the atmosphere. And the atmospheric distortions are larger than the shear distortions.
They don't average out over time?
No, so they just tend to smear things into circles. They actually just wash away the shear. And you can't just average it. Not to say that there aren't problems with space-based observations too. So there are systematics with that as well. For instance, charge transfer inefficiency. So when you're doing the readout from the CCD, there will often be a trail of charge left behind in the detector. So it'll give you these like weird trails to your galaxy images that creates a false shear in the readout direction. And that's something unique to space-based observations because those charge traps that are causing that trail are created by cosmic rays bombarding the CCD. And that's something that gets worse with time. And so these are things that, so ground-based and space-based sequencing are actually really different from each other. And there are teams of people who are working on measuring. And measuring the shape of the galaxies is a really hard thing to do. And so there are people actively working on this. And there are actually data challenges ongoing to try to figure out the best pipeline to get the shear out.
Any other questions? Jesus, thank Alan again.